Hi, and welcome to Psych 319, Chapter 13, Part 2. We spoke a bit already about problem solving. Now we're going to talk about reasoning. Slightly different. Um, psychology has very strict definitions for different constructs, and sometimes they use everyday language, but these two things are actually very different. Problem solving is the mental steps required to get from an initial state to a goal state. Reasoning is using specific rules of logic to solve problems. So this discipline really came out of philosophy, but the tradition has continued in psychology. And this comes from logic. In philosophy, reasoning involves making conclusions from a list of premises. So for example, if I make a premise, if computers can think, then they are alive. If this premise is true, you can make a conclusion. So the premises is, if computers can think. The antecedent is, rather, if computers can think, then the consequent is, then they are alive. So an antecedent and a consequence are sort of an idea that if a prior thing is true, then the latter thing must be true. And deductive reasoning is, what deductive reasoning is that you make very specific claims based on general observations. So you're going from general to specific. For example, if we have the premise, all cats are feline, then the conclusion, my cat must be a feline, must be true. We're going from a general observation, all cats are feline, to a specific one. Therefore, my cat must be feline. It logically follows, using deductive reasoning, that if all cats are feline, mine must be feline. Inductive reasoning is the opposite. It makes general claims based on specific observations. So if my cat has claws, we might induce that all cats have claws. You might already see the problem with this argument. So in deductive reasoning, we have what's called deductive validity. The conclusions depend upon the strength of the premise. If the premise is true, then the conclusion will be true. So for example, all cats have 20 toes is not a true statement, because we know that some cats have more than 5 toes on each paw. So some might have 24 toes total. So the premise is false, and therefore the conclusion is false. So the conclusion, the next cat I meet will have 20 toes, has weak deductive validity. Deductive logic is relatively safe because the premise can be scrutinized before coming to a conclusion, and you know the conclusion will be true if the premise is true. Now what you might have already seen in our previous example is that there's a problem sometimes with inductive reasoning. Inductive reasoning has what's called inductive strength. The conclusion is valid if the specific example is a good representation of the general. For example, let's say we make a specific observation. Every swan I've seen in my life is white. Then we might come to the conclusion, all swans are white. Well, you can see the problem with this. The next time I might run into a swan, it might be black. So the conclusion, the logic is, if all swans are white, then the next swan I see will be white. However, the first black swan I run into will invalidate that conclusion. So inductive reasoning is relatively risky because we never know if the conclusion is truly correct until it's disproved. So we can only know that it was incorrect. So when you're going from a specific observation to a general observation, you're always making a risk. And this is kind of how the brain works. We go through life and we develop schemas and sort of stereotypes for how the world works, and we maintain that schema until it's proven incorrect. Then we have to change the schema. So we can update our knowledge, but we're always kind of operating on a half-truth. And this is very important because all of science sort of rests on this premise. When we test a hypothesis in science, we use inductive logic. But because inductive logic is weak, we can never truly prove something in science. This also goes for courts of law. You can never prove anything beyond the shadow of a doubt, because there is always some alternate hypothesis. So we can only observe something and disprove something, but we can never truly prove something. All scientific theories are falsifiable. They can all be put to the test. And this is actually the beauty of science. It's flexible, it's adaptable, and it's constantly in search of truth. So we have some information now that we believe to be true, but it might be proven wrong in the future. But we can adapt, and we can adopt that new truth and change our scheme about how the world works. So, for example, the problem of proving things. Does Santa Claus exist? Well, a 6-year-old might think so. If you met a man in a red suit, does that prove that there's a Santa Claus? Probably not. There might be an alternate hypothesis. Maybe it's the Macy's Santa Claus. Maybe it's just a big guy with bad hygiene and poor taste in clothes. Even if you saw a guy flying through the air with reindeer, would you believe it? No, there's probably an alternate hypothesis. I think they do that every year at Disneyland around Christmas time. So you can see how definitive proof can be difficult. There's always some other explanation. So in deduction, going back to the strong case, in deduction, going from general to specific, we use what's called propositional logic or propositional reasoning. And it follows the formal structures of logic and philosophy. We use this kind of equation. If P, then Q. If we observe P, then Q must be true. So remember that if the premise is true, then the conclusion must follow logically. If all cats are felines, and we see a cat, then it must be a feline. So if P, all cats, then Q are felines, and we observe P, we see a cat, thus Q, it must be a feline. If it's followed correctly, it will always lead to a valid conclusion. So deduction is very, very strong. In everyday thinking, though, we sometimes make a mistake. It's called affirming the consequent. Now, the order of P and Q is very important. So if P, then Q, it should go, if P, then Q, we observe P, thus Q. But sometimes we make the mistake in affirming the consequent. We observe Q and thus conclude P. But those two are not necessarily related. The order is very, very important. So, for example, take this following statement. If I'm a genius, then I'll get an A in this class. Okay? If P, then Q. If I'm a genius, then I'll get an A in this class. I got an A. We observed Q, not P. Therefore, I'm a genius. If you get an A in class, does that make you a genius? No, not necessarily. You could have just gotten an A in that class. So, if you affirm the consequent, you observe the consequent, and believe that the opposite is true, the antecedent is true, you might be making a huge mistake in your logic. The order of these things are important. And we're often victims of illogical thinking because the structure of language sometimes leads us to a faulty conclusion. P going to Q is not the same as Q going to P. Here's another example. So here's the scene. Over here on the right, I've just got a little bit of a joke, a parody of Rock Band called Accordion Hero. Instead of Guitar Hero, you play the accordion. Here's the scene. I tell you this statement. If you don't stop playing that damn accordion, I'm going to slap you. Okay, so what do? Most of you would probably say, well, I'm going to stop the accordion. You stop playing. But then I walk up and I slap you anyway. Well, what was the problem with that? You thought if I stopped playing that you wouldn't get slapped. But there's a problem in that logic, and language sets you up for that problem. In this statement, it implies if you stop playing, you won't get slapped. But the truth is, you were going to get slapped no matter what you did. Stopping or not stopping wasn't going to change that. But what you did is you affirmed the consequence. So language establishes a false relationship between P and Q, and rather than preserving the necessary order, you observe one and you assume the other. This problem becomes even more complicated with something called syllogisms. So syllogisms work just like logic, except instead of involving absolute statements, it involves statements of probability, like some. Instead of saying always or never, we can say some, and that implies a bit of probability, which makes it complicated. So in propositional reasoning, if P then Q means P always accompanies Q, or Q always logically follows P. Syllogisms use a special language. So for example, all cats are feline. That's a logical statement. Some cats have 24 toes. Thus, some felines have 24 toes. And this is a true statement, and it's logical, but it's a syllogism because it uses the word some. Some is a probabilistic statement that often gets us into trouble. So all cats are feline, for example. Some cats have 24 toes. It's faulty to conclude that all felines have 24 toes. It's a false conclusion because a syllogism doesn't imply that all things fit into that category. So as I mentioned in the previous lecture, analogies are very useful for solving problems. If something's worked before, we tend to apply it in a new situation. However, there's a problem of always becoming functionally fixed or not seeing how a tool can be used in a new way. I'm sure if you've taken any standardized tests, you've seen this sort of analogy. Cat is to mouse as dog is to what? Cat. Well, that's a very simple analogy. And you can have these analogies that are picture-based. You can see if this is to that. Sorry, let me start over again. In this particular task, you might say, well, what is the figure that fits in the blank square? Well, you might imagine it has a black following from these two things. It might have a black something in its lower right-hand corner. Following from these, you assume it must be a diamond. So it somehow has to fit into that category. You can imagine what it is. I'm going to skip over this movie because I don't think it's going to play properly. So why do we care about induction? That's how the brain works. We are pattern detection mechanisms. We see what's around us, we make conclusions on it, and we jump to the conclusions based on what we see. Remember this example? How many of you now immediately recognize the dog? Chances are, if you saw the dog the first time, you'll see it again. If you didn't see the dog the first time, you won't see it again. We can remember patterns only after seeing things for a very brief time. We're constantly comparing input to our memories and making decisions. And many of these, oops, sorry, I have a computer issue going on. Okay. Many of these decisions are analogy-based decisions that compare the current problem to something in memory. But as we've seen, inductive logic is probabilistic and faulty. So sometimes making conclusions from your knowledge base to the general, the world, can be very, very weak. So what that means is we can't always count on our experience of the world being correct or being a correct representation of how the world really works. Going back to hypothesis testing in science and so on, so after we've developed a pretty good scenario for how something works, we develop a schema that can be tested. So what's the next in this series of numbers? 1, 2, 3, 5, and 8. If you figured it out, it's 13. You take the first number and you add it with the second to get the third. And 2 plus 3 is 5, and 3 plus 5 is 8, and 5 plus 8 is 13. This is a series of numbers called the Fibonacci sequence. And you can see this demonstrated in this science thing. Each rectangle here is the sum of the previous width of the rectangle before it, and so on and so forth. If you connect the diagonals in all of these, or the corners with a spiral, you get this conch shape. You can find it in nature again and again and again. So we don't always use hypothesis testing, though. Some things are easily tested, some things are not. Some things have heavy consequences for failure, and some do not. So for example, picking your favorite flavor of ice cream is a relatively easy thing. You can try a bunch of flavors of ice cream and then to figure out what is your favorite. You don't have to really use inductive reasoning. You could just use trial and error. However, picking your life partner has a huge and heavy consequence. So you're going to want to make the best inductive conclusion you possibly can. One of the problems in inductive logic is called confirmation bias. We tend to look at instances that confirm our schema for how the world works rather than looking for things that disprove it. So let's say you're a racist, which I'm sure you're not, and you come up with some terrible conclusion that all Hispanics are lazy. I'm Hispanic. If you go through the world looking for that evidence of that, you might say anytime you see somebody who looks Hispanic taking a nap, you might say, oh, well, that's evidence that all Hispanics are lazy. And this is indeed how stereotypes are reinforced, particularly negative ones. People collect evidence for the belief they already have, when they really should be looking for, oh, maybe Hispanic presidents or people that invalidate their belief system. But we're always looking to make ourselves look good and looking to confirm the biases we already have. And that's a dangerous thing to do. So again, remember, all swans are white until you see the first black swan. So other ways we make errors in judgment, in addition to confirmation bias, sometimes we have a poorly presented premise. We don't really understand the way the premise is stated, and so we can't make a conclusion from it. Negative statements are very hard to understand. So for example, if I say something like, if not P, then Q. If you don't stop playing the accordion, then I'm going to slap you. Sometimes things like that might be hard to understand. Modifiers that change absolutes, again, are also makes things difficult, like some. Sometimes the premise can be perfectly stated, but we misinterpret it because we're not paying attention or something. Again, that example. If you didn't really understand the full possible consequences of the premise, then you might make a faulty conclusion. Another problem is the failure to consider all possibilities. If I make the statement, some York students are musicians and some musicians are insane, does that mean that some York students are insane? Does that mean all York students are insane? If you actually look in your book, there is a description of this. There's actually 45 possible combinations of making a conclusion from this statement. And I'm not going to go into much detail here because the book does a better job of it. But we don't always consider all the possible combinations of students and musicians and insane people. And that's a difficult thing to do on the fly. And that's with only 3 combinations. Think about if you had like five different personality aspects to evaluate. You'd have so many possible combinations, you wouldn't be able to consider, like, there could be thousands of combinations. And that would lead to an error in judgment. Sorry, I misspoke. There's 41 combinations of A, B, and C. Continuing, we also have what's called believability effects. So remember, language and experience can influence how we interpret things. If we falsely interpret the premise, we're likely to make a false conclusion. So here is a logical statement. Most doctors are workaholics, and most workaholics end up divorced. Do you believe that? Do you believe that most doctors get divorced? You might jump to the conclusion that most doctors get divorced because the language sets you up like that way. However, maybe doctors are only workaholics that don't get divorced. So you're sort of jumping to conclusion because the language sets you up for that fall. But let me give you the exact same logical statement, but with a different scenario. Most pets are cats. Most cats live in the wild. However, we don't conclude that most pets live in the wild because this is oxymoron. This is oxymoronic. A pet, by definition, doesn't live in the wild, so it doesn't make sense. A doctor, on the other hand, can get divorced, so you might jump to that conclusion. The logic, though, if you look at the logic and the way the sentences are structured, they're exactly the same. Another way we can make an error in judgment is some puzzles are difficult if we don't know the material. If we're a novice in a field, or unfamiliar with things, it makes it difficult to come to a reliable conclusion. I'm going to skip these examples, but they're puzzles, and you can try and solve them. I won't give you the answer, but they're logic tests to see if you can use hypothesis testing to find the correct answer for this. And you might find the correct answer in your book or on the internet. And these are in the slides. All I can say is that the EK47 problem is basically very similar to the pass-fail problem. So how do we reason? There's various theories. There's a computational approach, the idea that the brain makes all decisions using similar processes. You can look at the time course of problem solving. The solution to problems is thought to occur in stages that can be measured. So imagine that you're thinking about something complicated. You can have multiple processes that are involved. You can time each individual stage of that process and then determine what process comes before another one. For example, if the problem has 3 steps to be solved, like perceptioning, reasoning, and executing the solution, you might be able to measure just reasoning or just perception. You can take a stimulus, A, reasoning, B, and execution, C. And if all of those take 15 seconds, but then you swap out a new stimulus and you say you swap out stimulus D for stimulus A, but keep the other 2 parts the same, reasoning and execution, and you find that the whole thing now takes 20 seconds, you might make the conclusion that it takes more time to encode stimulus D than stimulus A. So assuming the responses were held constant and the stimuli were relatively easy to encode, this approach allows us to measure steps in reasoning. And this is how we determine that you shouldn't be able to make multiple decisions at the same time. When a person is, we covered this in attention, so I'm not going to go into it, but remember that if a person is trying to work on 2 tasks at the same time, there's a bottleneck. And if you're doing 2 tasks and you need to make a judgment in task 1, you can't make a judgment in task 2 unless you're finished making the judgment in task 1. And so this sort of computational approach allows us to measure different stages in reasoning. And it turns out that most problems we have from reasoning start from faulty encoding. We don't understand the problem, and therefore it's difficult to make a decision and execute on that. Another idea is the rules heuristic approach. The idea that the brain is a big bag of tricks, and we use different cognitive processes for different tasks. We use different modular processes is another way of saying it. So you might have a brain module dedicated to language and a brain module dedicated to math, and the math only works on the math problems and the language part of the brain only works on the language problems. And it depends on what context you're in. So different contexts imply different logical rules. Forget this example, it's not very clear. I usually have to demonstrate this in person. And so most problems arise from not interpreting the context correctly according to the rules heuristic approach. The mental models approach assumes that mechanisms for all logic are language-based. So whether you're doing a math problem or whether you're doing a language problem, everything passes through the filter of language, and therefore language is the determinant of logic. So we use the same mechanisms for problem solving as we would for building a prototype of a word. We start with something simple, a concept, a linguistic concept that identifies something in the world, and we develop a schema around that concept, and the more exposure we have to different variations of that, the stronger that concept builds. So for example, if you trying to identify what a cat is, the more cats you see, the stronger the notion of the concept and the word cat becomes. When we listen to speech, we're building a mental model of a scenario. The same process is thought to occur for problem solving. And so errors in reasoning are thought to result from poor model construction, not considering all the possibilities, and some of the other similar problems that we saw in the other models. There's some neurological evidence for logic and reasoning. I do not know where my words went on the slide, but the general idea is that when you work on certain types of problems, different parts of the brain tend to light up. And that seems to think that, it seems to suggest that we are using some kind of modular approach, that the brain might indeed be a bag of tricks, and that certain processes serve certain problems better than others. Here are the words. Okay, so yes, this basically says exactly what it was, and even though language areas do become involved in language tasks, and then spatial. Okay, so people were given a task, and the task was the same. The problem was the same, but the task was different. And what they found out was that if the task was linguistic based, language areas became activated. If the task was spatial based, then the right hemisphere and areas responsible for spatial reasoning became activated. And so this seems to support modularity, or the rule heuristic and mental models approaches. Okay, this is something we can skip, and we can also skip this. This is another puzzle, and this is another puzzle. So you can solve these puzzles if you want to test your logic and reasoning skills. But that's it, and I will see you in the next chapter.